Welcome back, biologists. We are in our final lecture. This is Chapter 38, Part 2 on human impacts. This is a supplemental lecture, just like the last one. A lot of the information in this lecture you will not necessarily find in Chapter 38, so for the final exam, you are responsible for both the contents of what is in Chapter 38, that is what you read in that chapter and what you're quizzed on, and also on this lecture right here on human impacts. Now, the first place we're going to go with this is in overconsumption. And really, this whole lecture is going to focus on how humans impact the biosphere. And we're going to hit on a few of them. Certainly we don't have the time to cover every single one, but I wanted to start off with this story. It's actually quite an interesting one on the use of plastic bottles in delivering water. You may ask yourself, these are actually really good questions. I asked myself these questions when I was researching this. Where does plastic come from? How is plastic made? And in particular, how does this pertain to plastic bottles? Well, it turns out that plastic bottles don't come from a plastic tree, and they certainly don't grow in the ground. If you want to understand where plastic comes from, you need to take it all the way to here. It turns out that plastic is an oil product. And what is oil then? You should ask yourself that next question. Well, is it organic? Is it organic? And if it's organic, does that mean that it's natural? Does that mean that it's good? These are all really good questions. Well, it turns out that that oil is very, 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 very old. And you're looking at an oil platform here. And let's first start out with this. Where does oil come from? Well, it comes from ancient organisms. I'm showing you a picture here of a dinosaur, but ultimately dinosaurs and living animals like that really only made up a small fraction of the actual oil that we use in our cars and in our trains and buses. Actually, what I want you to focus on is the forest behind this dinosaur. You see, way back when, before the Permian extinction, right around 250 million years ago, the planet was really covered by a gigantic forest. And what is a forest? Made up of lots and lots of plants. Well, lots and lots of plants means you have a lot of photosynthesis going on, which means that carbon that was in the atmosphere over the course of tens of millions of years is getting sequestered and locked up by trees and turned into solid carbon in the form of bark, wood, root structure, and leaves. And you know that even though, as we learned in the photosynthesis lecture, that plants actually photosynthesize in the daytime and then respire at night, you know that it's still a net positive gain in carbon because the tree actually grows over its lifetime. It's actually accumulating carbon as it grows. And then when a tree dies, it falls down to the forest floor and gets degraded. But and then as it's degraded, that carbon actually gets reincorporated into other things, eventually worked up through the system. But if you have this process going on over tens of millions of years, beginning about 300 million years ago actually, right around that time, then you get this accumulation of carbon, which eventually gets sequestered in rocks and put under pressure, and over long periods of time it becomes oil. So here we go. We have a dinosaur going extinct. So from about 300 million years ago until about 65 million years ago, or just before that time, all of this organic matter on the planet that has been living and dying and living and dying and eventually sequestered in the ground and put under heat and pressure, that all of that is going to be locked up in rock. So oil is actually hundreds of millions of years old. The oldest oil, so the real premium stuff that we prefer to look for and that we prefer to use for our vehicles, is actually about 360 million years old. That's a very long time. And the youngest oil is 80 million years old. And just to put that into perspective, keep in mind that the dinosaurs went extinct about 65 million years ago. So the youngest oil is actually still a little bit older than the dinosaurs when they went extinct. That's old stuff. And part of the problem is that as long as it takes to make the oil, we're using it on a time scale that is not consistent with the time scale in how you make that oil. So now we're going to sequester that under rock, either under the rock on the land or under the rock in the bottom of the ocean. Most of the oil that is available on land, the easy stuff to get, we've pretty much gotten it all. The only oil that is left on the planet is stuff that's actually hard to get, like, for example, on the bottom of the ocean. So now let's come back to our oil platform. Let's think about what we actually spend in order to get that oil out of the ground. We spend hundreds of millions of dollars building these very large structures, right? These big platforms that are essentially attached to the bottom of the ocean, in some cases hundreds of feet, but in other cases thousands of feet down to the bottom of the ocean. We use huge amounts of energy to withdraw the oil out of the ground. We use large amounts of energy to transport that oil all around, and ultimately you have to ship it somewhere. And so these are the oil tankers that oil gets shipped all around the world in. And these are essentially floating cities. And if you don't believe me, we can actually just count from here's the viewing deck. So we'll go up one above there. This is where you could stand up at the top. So that would be like 1, 2, 3, 4, 5, 6, 7, 8 to the deck. And then there's actually decks below that. So that would be 9, 10, and actually 11 right down to the water line. That's like an 11-story building. That is a huge, huge ship. And so these things are carrying so much oil that we don't really measure it in just pounds. They actually come up with their own terminology for it. They call it DWTs, or dead weight tons. And so a typical carrier is, the smaller ones carry about 10,000 dead weight tons, but something like this big monster in the background here carries about 550,000 dead weight tons. That's a lot. Now, keep in mind also that obviously you're not burning gasoline to drive these things around. It wouldn't make sense to drive gasoline or to carry oil, but then to burn gasoline. That's the equation doesn't work out properly that way. So instead, we have to burn a really bad or really low grade of oil. In this case, we're burning bunker fuel. And bunker fuel, which is also known as heavy fuel oil, is extremely inefficient, but it's extremely cheap, which is how you can get away with burning that and shipping things around the world and not cutting into your profit. So it's very inefficient. In fact, it's about 1,000 times less efficient than burning gasoline. And if you wanted to put its fuel efficiency into perspectives that you might understand, the miles per gallon for this kind of vehicle is getting about 0.008 miles per gallon. Well, that's really a hard number to process in our brains. So you could think of it this way: 42 feet per gallon. In other words, you have to burn a gallon of this bunker fuel just to move that ship 42 feet. Or, in gallons per mile, it would be 125 gallons that you have to burn just to go a single mile. And since you're burning this incredibly inefficient fuel and you're dumping huge quantities of gas up into the atmosphere as a result of that, air quality definitely goes down as a result of this, with lots of sulfates and nitrates being dumped into the environment. Now, this is assuming, by the way, that you're able to transport that oil without having any problems. Of course, we know that there are problems. There are always problems. And I want to remind you about one of those problems that happened back in April of 2010. Please, please, please commit this to memory and never forget that 2 days after Earth Day, on April 22nd, the platform Deepwater Horizon in the Gulf of Mexico exploded, killing people and creating the worst man-made environmental disaster to ever strike a U.S. coastline. We are still feeling the after effects of this one, and your grandchildren will also still be feeling the after effects. So please commit this to memory and remember that these sorts of things happen. This particular one was a huge disaster, and so it made news for months, but there are much smaller disasters that are occurring on a daily basis that are not big enough to be newsworthy. Now, this is one instance, but it happens all over the world. Simultaneous to the Deepwater Horizon oil spill, there were other oil spills that were occurring in the world at the exact same time, and the only reason you didn't hear about it is because the Deepwater Horizon BP oil spill was dominating the news at that time. But these things happen all over the place. Here are some volunteers in Korea that are doing their best to clean up an oil spill that invaded one of their beaches. And you know what? They're doing a great job, but no matter how hard they try, they are not going to get all that oil up. Some of that's going to be left behind in the environment, and that's really unfortunate. So, okay, all of this aside, let's assume that you do manage to get your oil to the refinery. This is the refinery, and this is actually one locally to us. In the refinery, essentially what you do is you do what's called fractal distillation, and in a nutshell, what that means is you take that crude oil, the stuff that's really unprocessed, and you put it into a big distillation chamber like this. And then you apply huge amounts of energy underneath it by heating it essentially to get this thing to separate out with the really light stuff on the top and the really heavy stuff on the bottom. And this is kind of what it looks like. You've got your light stuff up here, like your jet fuels and your fuel burners and even gasoline. All of that's kind of up here. And then at the bottom would be things like tar and asphalt. Both of those are very dense fractal processes. But somewhere in the middle is the grade of petroleum that you use in order to make plastics. So let's assume that you essentially climb up these ladders and you stick your straw in right there, right in the middle, and that grade of oil you then suck out. And you use that to create plastic beads. These are called nurdles, and that's an actual official term. A nurdle is one of these pre-plastic beads. And you might ask yourself, well, how do you go from like oil to that? Well, I can't tell you because it's a trade secret. It is proprietary information that only the plastics industry knows. But essentially what they do is they take oil and they chemically treat it to turn it into a polymer like this. And once it's in this really light polymer stage, which by the way can blow all over the place, it then can be colored and molded just like this. Of course, here's what the molding machine looks like, and it uses huge amounts of energy to essentially heat the plastic, but not too hot, but hot enough that you can then mold it and run it through a molding machine like this. Okay, great. So we've just created a plastic bottle. Are we ready to put water in it and drink it? No, of course not. You see, because it's an organic compound, oil is an organic compound. It's dead organic matter, essentially. It is ripe. It is perfect for bacteria. So what you have to do first is sterilize the plastic. Here's the sterilizing machine. And, of course, this, too, uses huge amounts of energy. All right. Now we're ready to put water in it, right? We've sterilized it. Boy, if you're going to go through all of that hassle, you're going to be pulling oil out of the ground from thousands of feet below the surface of the ocean. And in fact, once you get down to the bottom, now you're penetrating even more thousands of feet into the bedrock to pull that oil out, to ship it all around the world with the potential of having environmental disasters. You spend all of that energy creating a plastic bottle. Well, if you're going to stick water in it, wouldn't you think that the water should be like super water? It should be the best possible water you could ever put into it, right? You'd be wrong. Actually, it's usually tap water. It's usually municipal tap water. In the case of Dasani or Arrowhead or any of these other water bodies, even if they are run through a filter, usually they're using it by running it through a municipal water source that is then run through another filter. In fact, the filtration system that you see down here on the lower left is actually just something that you could probably buy at Home Depot. Theirs might be a little bit more fancy, but the reality is there is rarely ever special water in any of these plastic water bottles. Okay, again, municipal tap water most of the time. Okay, well, now you're finally ready to drink, right? So you're going to go ahead and drink. You're going to hydrate yourself, right? Great idea putting it in a plastic bottle, right? That's the only way to get good water, or so you think. But now we drink, and then 2 hours later, where's that water going to be? Well, if you're like me or anybody I know, you're essentially either going to be sweating that water out, breathing the water out, or peeing the water out. That's right, water doesn't stay in your body for very long, which is why you have to continually replenish it. You're constantly having to drink water. So let's do a nice comparison here then. We're looking at time and energy versus filtered tap water. That is filtered tap water of your own. You could go out to Home Depot, put a filter on your tap water, which, by the way, your tap water is really, really good for you. I'll explain why later. And you're going to compare that to the time and energy that goes into making a plastic bottle. So let's start off with here. Hundreds of millions of years to make the oil. Use energy removing it from the ground, use energy transporting it all around the world, use energy to distill the oil, add chemicals to make nurdles, use energy molding the plastic, use energy cleaning the plastic, so that 2 to 4 hours later the water can just pass right through your body. Okay, this is not a good representative equation that you should follow if all you're trying to do is hydrate your body. If all you're trying to do is hydrate your body, is it also necessary to create plastic trash? Well, there's more to the story, turns out. What happens next in the life of a plastic bottle? Well, what do you do with a plastic bottle after you use it? I know that you're probably telling yourself, I recycle it, right? Well, unfortunately, not very much of plastic actually gets recycled, only about 5 to 10%. That's it. Which means that the vast majority of plastics are going right into the landfill. And keep this in mind also, for most plastic bottles, the bottle top is not even recyclable. Think about that Coca-Cola bottle that you drank the other day. The red top, yep, not recyclable, only the bottom part. The red top part automatically goes to the landfill. And here's another kind of kicker. You might think to yourself, well, I'm being at least conscious when I recycle. I don't know what anybody else does, but at least I recycle. Well, you're probably thinking in your mindset, well, I know what recycling is. That's when you take something, you melt it down, and then you turn it back into that same thing again, right? Like an aluminum can. You melt an aluminum can down to aluminum, you recast that aluminum, and now it's an aluminum can in the future. And you probably think, well, if I'm doing that with a plastic bottle, that must be what's happening there too. And that's actually not what is happening. You see, plastic is very delicate stuff around heat. So the act of melting it down to create more plastic actually ends up denaturing the quality of the plastic. You can never turn a plastic bottle into another plastic bottle in the future. The only thing you can do is melt the plastic, degrading its quality and turning it into a lesser plastic product. That's right, plastic bottles are not recycled. They are not recycled, at least not by the definition you thought of it. The proper term is they are downcycled. When they are put into the reused waste stream, they are usually melted down and turned into something else. Like, for example, reusable wood, or they actually mix the plastic into that, or T-shirts. You can turn them into T-shirts. You can turn them into parking bumpers. There's lots of things you can turn it into, but you can't turn it into another plastic bottle. If you want another plastic bottle, what do you need? What do you need, right? Melting degrades the quality. So if you want another plastic bottle, you need more oil. Okay, that's just the reality of it. Now let's talk about decomposition and put the plastics issue into kind of a comparison. Here we've got a banana, and you're going to eat this banana. You've got your banana peel. Let's do this experiment out in your backyard. If you were to bury that banana peel and then come back at some point in the future, how long would it take for that banana peel to completely disappear and no longer be a banana peel? The answer is about 3 weeks. Not bad, right? You bury a banana peel, 3 weeks later, it's not there anymore. What about this cardboard box? About 2 months, right? 2 months, so you could do that experiment in your yard too. You could even do this one. These are wool socks. And it turns out if you bury wool socks in your backyard, you can come out 1 year later, and those wool socks will have degraded and gone back into its organic and inorganic parts that have been broken down. Okay, now let's talk about some longer term ones. How about this? These are aluminum cans, and as I had mentioned, aluminum is fully recyclable, right? But what if you were to bury this in the backyard? How long before that aluminum can disappears? The answer is 80 years. That's right, that's a long time, isn't it? Of course, most people aren't burying aluminum cans and having them decompose. They are recycling them, which is perfect, which is what makes aluminum cans actually the best medium for this. Far better than glass, far better than plastic, because they are actually recycled, and the amount of energy that goes into that recycling is less than the other kinds of recycling methods that we will talk about in a little bit. What about this one, plastic water bottles? The answer is 500 to 1,000 years. That's a long time. Think about it. How long was that water in your body? A couple hours? So a couple hours for that water to be in your body is that justification for creating a trash item that will remain in the environment for at least 1,000 years. And just for comparison, here is a styrofoam container, something that you would get from the 99-cent store. You're going to a park, you're going to a party with a bunch of friends, and you forgot to bring your cooler. You got your drinks, and so you're just going to stop in the 99-cent store and buy one of these for really cheap. And you put your stuff in there, and you're good to go, right? But what if it breaks? Who cares? It only cost me 99 cents. Except that these styrofoam containers are in the environment for more than a million years. Now, why can't we nail down an actual date? Because we don't actually know. Based on the degradation rates, we can calculate it out, and we know that it is at least over a million years old. It's incredible how bad that is. Because the amount of time that it will be in your hands using it is a very small fraction of the amount of time that it will stay around in the environment. So what do we do with all these plastics? What can we do? Well, even if we're trying to recycle as much as we can, of course we know that's actually downcycling. Some of this is going to get away from you because plastics happen to be very light. So this happens all the time. On our local beaches, right after a storm, or right after a big event, like after the LA Marathon, you just go down to the rivers there by Ballona Creek up near LAX, and the rivers are just loaded with plastic cups and all kinds of things, and that all ends up on the beach there. So it's pretty ugly. And okay, so does it just come off our land and get washed up onto our beaches? No, unfortunately not. That's not where it stops. The plastic is insidious, and it ends up entering the ocean proper. So let's take a look at a map here. I'm showing you a couple of things here. Here's the islands of Hawaii, okay, and then here's our coastline up here. I wanted to show you some pretty ugly pictures. These are actually bird carcasses, and you'll notice that there's no more flesh really on these carcasses. What has essentially happened is the soft tissue has all degraded away. All that's left is feathers and bones, and then the gut contents of what used to be in the stomach. In this case, in both of these birds' cases, you're looking at guts absolutely loaded with plastic. I'll tell you now, these are Laysian albatross chicks. These aren't even adult birds. And I'll explain that in the next slide. But you might ask yourself, well, where did these birds pick this stuff up? Were these birds like foraging near shore, right? I mean, here's where we are. We're basically right about there. Were they foraging over near Seal Beach or Huntington Beach or San Diego? No, it turns out these carcasses are from French frigate shoals, a remote island that is actually remote away from Hawaii even, but it is one of the most remote islands on the entire planet. And yet, out in the middle of nowhere, where there are no people, birds are dying because of the overconsumption of what they perceive to be food. And it turns out it just is plastic. Here's another albatross chick, and here's a worker from NOAA, the National Oceanic and Atmospheric Administration, and she's performing a necropsy of this chick. And once she kind of opens it up, she's then removing all of the plastic bits that were in its stomach. So how did those plastics get in there? That's a chick. All right, well, when a mother actually gives birth to her baby chicks, she then heads off and begins foraging in the surface waters all around the island. And she is the product of millions of years of evolution. These birds are surviving by going out to the ocean and foraging on squid, fish eggs, fish swimming at the surface, and lots of other floating organisms. They gorge themselves on it, fly back to their babies, and then regurgitate all of that food directly into the baby's gut. Okay? So that's where this chick is getting all that plastic. Its mother is feeding it to it. And again, this is a strategy that has worked for these albatross for millions and millions of years. Only in the last 50 years have these birds encountered any plastic. But because plastic does not degrade and go away, it simply stays out there in the environment, we are accumulating every year more and more and more plastics, until essentially we're going to fill the oceans up with plastic. So how does it get there? Well, it gets there by lots of means, right? But essentially it's all coming from land. Now you might think to yourself, well, I wouldn't be the irresponsible one to let my plastic bag go, like this one right up here. Well, you know what? If you're using 100 bags and you're holding them all in your hands because you're going to do the right thing about taking them down to the recycling center, but one of them gets away from you, yeah, you may chase after it, but maybe you won't. Because you've got 99 other ones. You're still doing a good thing, right? Well, yeah, if everybody thinks that way, though, then that one little bit of trash ends up accumulating and becoming lots of trash. And lots of trash. I'm very serious about that. I've seen places where it's this bad. And wildlife end up encountering this trash. Here's an organism that doesn't have opposable thumbs to be able to reach and pull this piece of plastic off its head. And so it will eventually die as it grows and the plastic bag around its neck does not grow. It will end up constricting the animal's breathing, and the animal will eventually perish. So, over the last 50 years, plastics have been accumulating in the open ocean in what is now known as the North Pacific Garbage Patch. It is an area in the North Pacific, north of Hawaii, that has been accumulating huge, huge amounts of trash. And we now know that the North Pacific Garbage Patch is just one of 5 different trashy gyres that are just loaded with plastics in the open ocean. And so what I want to refer you to is a video that I posted up on the course website from the Today Show on plastic use and the North Pacific Garbage Patch. So take the time to watch that video. It's really quite amazing. It's true that every piece of plastic that was ever created so far in the history of the human species is still on the planet. It never goes away. And that's kind of frightening because it's designed to not go away. But there are people who are doing things to make a difference, and I wanted to show you a couple of people here. This is the House Rep John Garamendi, who was our former Lieutenant Governor in California. And I also am pointing at another guy over here by the name of Charlie Moore. Charlie is actually the guy who's featured in that video. And also, for those of you that watched the movie Tapped, Tapped is all about the plastic water bottle industry. So if you chose a different movie for your documentary assignment, go check out Tapped. You might really enjoy it, but Charlie is actually featured in that movie, and that's me. So this was a Santa Monica Bay fundraiser of about 5, 6 years ago or so. Okay, now there are other issues with plastics. It turns out that plastics, because they are organic compounds with lots and lots of carbon in them, they end up becoming a template for chemicals to either latch on or be released from. And there are many things that plastics will release, including things like phthalates, PBDEs, and nonyl phenols. These are all carcinogenic materials. And then, of course, they're also accumulating chemicals as well, like PCBs, DDT, and then a congener of DDT, DDE. So, plastic debris out in the middle of the ocean is accumulating all of these things at the same time that it is giving off all of these. And I wanted to focus on one of them in particular. This is bisphenol A. Some of you may have heard of it. The thing that makes this so dangerous is that it actually is a chemical that mimics estrogen. Biochemically, it looks just like estrogen, and your body behaves in contact with it as though it is full-on estrogen. And bisphenol A is also known as BPA. It is the substance that gets added to the plastic mixture to make the plastic malleable. And, certainly nobody has ever claimed that bisphenol A will kill you. But, the reality is it may not kill you, but it certainly does cause what are known as sublethal effects. That is, they affect you in ways that are really bad, just not so bad that they kill you. 93% of Americans have some PCB or bisphenol A in their body. You probably have some bisphenol A in your body. On average, we have about 2.7 parts per billion of bisphenol A. And I actually put the reference here. This is Sexton et al. 2004. The only reason I put this here, you don't have to download this paper or anything, but if you're interested in learning more, here's the resource. You can actually go and check it out. The United States has arbitrarily set a safe limit of 50 parts per billion, right? Well, that must be good, right? Were they doing that based on research? Of course they must have, right? Well, no, actually they didn't. They set it arbitrarily, and it's just a coincidence that it happens to be an order of magnitude bigger than the number that is in all Americans on average. Just so that you know, other nations have set their own safe limits arbitrarily also. Canada sets theirs at 25 parts per billion. But we also know from animal testing that 30 parts per billion can actually create ADD-like symptoms, attention deficit disorder-like symptoms. And we've also been able to witness DNA damage at 20 parts per billion, insulin resistance at 10 parts per billion, and at 2.4 parts per billion, which is now at the same level here, if not a little lower, you can actually induce sexual developmental problems in laboratory animals. And this is actually kind of frightening because who are experiencing or taking in a lot of this BPA? Well, adults are certainly, but so are children. Now, you could probably imagine that the hormone levels in young children, infants, let's say, or even those that are entering puberty, the concentration of estrogen in your body is essential. It has to be right on, right? It's telling your body when it's time to do all kinds of body functions, to change and to grow. And if you are sending huge amounts of bisphenol A through a developing child's body, you could seriously be messing up their development. There are some anecdotal accounts right now, and although the evidence is growing, that there may be a connection between the exposure of bisphenol A over the last 20 or 30 decades and the um, uh, the the development of puberty in girls, in young girls, at a younger age. So instead of girls going through puberty at the age of 12 or 13 or 14, they're now going through puberty at the age of 10, 11, or 12. So we're seeing a shift, and there are some people that are beginning to see a connection between these things, although certainly more research does need to be done. Okay, and here's another frightening thing, is that we're talking about developing kids here, infants. Infants, it turns out that many polycarbonate bottles that are used for baby formula also are high in BPA. Now, Senator Dianne Feinstein um, has introduced legislation to prevent that. And so I urge you all to check up on that to see if that has actually happened. What a lot of young mothers are opting to do now is, instead of using plastic bottles for their babies, they go back to glass bottles, just like their parents experienced. Turns out glass bottles are perfectly safe to use. They just happen to be heavy and they break, but otherwise they don't, at least they don't toxify your kids. Okay, so we're going to come back to our equation here that we brought up before, but we forgot to add some things here, like thousands of years for the plastic bottle to leave the environment, that is for each plastic bottle, and also let's not forget the long-term damage to people and the environment. So what are we going to do? I mean, this is pretty bad. We need to stop using plastic water bottles. If you're only trying to hydrate yourself, well then get a reusable bottle. Preferably a metal container or even a glass container that you can reuse, and fill it with water from your tap. Municipal tap water happens to be among the safest water on the planet. Again, I urge you to watch the movie Tapped. It's a great documentary and an expose on the plastics industry. Plastic water bottle manufacturers, those that make water bottles, are not beholden to the same rules and regulations that municipal waters are held to. Municipal water bodies or municipal water providers have to check their water hourly, essentially. They check the quality every hour. And they have to report that to the public on their websites, or they send it out to their clients. But not so with the plastic water bottle industry. They do all of their own monitoring. Okay, so nobody's forcing them and nobody's watching them. Okay, they're doing it themselves, and then they get to report their own data when they feel like it to regulators, and that's just not the way that it is supposed to be done. By the way, if you're a smoker, just a reminder: I'm not here to tell you whether you should or shouldn't smoke. I'll leave that up to you. You're an adult. But at least realize that cigarette butts, they are trash. That's right, you throw them on the ground, they are not going to biodegrade, they're not going to disappear. And that's because the cigarette filter, the part that you put up against your lip, that's actually made from cellulose acetate, and that is a type of plastic. So keep in mind, what is a filter trying to do? Well, a filter is designed to remove all of the toxins and a lot of the soot and other materials that you don't want to breathe down into your lungs, oddly enough, when you're smoking. Well, if it's doing its job, then it means that each one of those filters is actually a little poison pill that is loaded with all the stuff that it has filtered out from the burned cigarette. So when you throw one on the ground, you're essentially putting a toxic pill on the ground. And you know what? You can do this experiment yourself. I call it the goldfish experiment. Go outside, find some cigarette butts. Trust me, they're easy to find. Just look in the gutter. They're everywhere. Grab like one or two or three of these cigarette butts, take them home, and throw them into a gallon jug of water. Okay? Leave it there for about 2 to 3 days. And then take a goldfish and throw it into that jug of water. That goldfish is probably going to die within a matter of 24 to 48 hours. And if it doesn't die, it will develop some serious problems on the surface of its skin and its scales. until it eventually will die. It just takes a little bit longer. And that's because of the toxic nature of the water in which it's swimming. As the result of just a couple of cigarette butts, there are tens of millions of cigarette butts that are thrown all over the ground every single day. And if one of those butts is able to foul 1 gallon of water, you can only imagine how much water gets fouled just by cigarette butts. So do us all a favor. No butts on the beach. Okay? No butts on the beach. Alright, so you might ask yourself, well, what can I do? Right? I'm just trying to be a conscious consumer. Sometimes I'm ignorant, but now I'm learning. So what do I do? Well, you're going to follow this rule, and I'm sure you've seen this sign before, and you're probably saying, oh, I know what that sign means. It means recycle, doesn't it? Well, I'm here to tell you something a little different. We're going to go beyond recycling. This is not the recycling symbol any longer. Here's what it means. Number 1, reduce. Number 2, reuse. And number 3, recycle. And so you are now going to go out and educate others, because this is where we're going to focus. We're going to focus in reducing and reusing. Is recycling good? Yes. Yes, recycling is very good. But it is less important than reusing items. And reusing items is even less important than reducing. First and foremost important thing that we need to do is to reduce our consumption. So you're going to be learning it in this order, and you're going to educate others. You're going to say reduce, reuse, recycle in that order. Okay? Very, very important. All three are important, but this one here, reducing, that's the most important, because that's the most effective. Well, how do you reduce? What do you think? Well, there's a lot of ways that you can reduce, like don't use so much stuff. You're just trying to put food in your body. Is it also necessary to make trash as a result of putting food in your body? No. Pay attention to the amount of packaging. If you see something that is overly packaged, don't buy it. In fact, do a better thing and write a letter to that company informing them that you did not buy their product because of the amount of packaging they had. Get off junk mail lists. That's another good one. I happen to like that one a lot. Use less energy. Find a way to sit next to a window and read during the middle of the daytime. Is it necessary to put on a light when there's perfectly good sunlight right outside? Use less water, too. We're going to talk about, we talked about water issues before, so you may want to revisit that to learn the merits of why you should use less water. And I think most importantly is once you kind of find a way to live your life where you're actually being able to do this, tell other people about it. Get them to do it too. Well, what about reusing? Well, there's a lot of ways that you can reuse. You can reuse using a Nalgene bottle like this. In this case, you're not creating trash, you're simply reusing something. I prefer to use metal containers and glass containers, but if all you have is a Nalgene bottle, that works fine too. But just make sure that you look for a reusable container that is BPA free, that does not use BPA. And you need to cut back on disposable items. I mean, things like plates and, well, I put silverware here, but I really meant plasticware. Stay away from plasticware. The one-time use forks and knives are absolutely idiotic. A plastic fork will be touching your lips for about 20 to 30 minutes, and yet it will sit in the landfill for 500 years. That does not make sense at all. I mean, we can hardly remember the meal we had last week, let alone the fact that we used a plastic fork that's going to be in the environment for 500 years, long after we have forgotten about the fork, or even the meal that it was putting into our mouth, right? So get your reusable containers, and now I want to actually mention gray water recovery, because I mentioned that last time. Gray water recovery is a really great idea. It's a way to reuse water, right? So you use water to wash your dishes, or to wash yourself, or to wash your clothes. Well, as long as you're not using harsh chemicals, well, then that stuff can actually be used to water your plants. Okay, use that water twice. That's my advice to you. So, refill your bottle. use filtered tap water. You don't like the way your tap water tastes? Well, it's probably because of your pipes, not because of the water. So put a filter on it. That will actually solve your situation. Okay, so that's the end of the plastic water bottle story. I now want to switch gears and look at foreign oil. Because we've talked a little bit about utilization of resources, and we are definitely addicted to oil in this country, and certainly as a globe, the human race is addicted to oil. So you might think to yourself, well, heck, if we're trying to get off of oil, we're trying to get ourselves away from that, why don't we just, I don't know, invent an agency or something like that that's going to help guide us that way, right? Like, we should have some special government agency whose job it is to get us off of foreign oil. And this agency should think innovatively. It should de-emphasize oil. It should start looking at wind and solar and lots of other really weird and interesting things, and efficiency. Well, yeah, the reality is, I want you to think about this for a second. We do have one. We do have such an agency. It's called the Department of Energy. The Department of Energy was established in 1973, and I realize that many of you were not, alive in 1973, but some of you were, and some of you were actually probably driving in 1973. And if you were doing that, I'll ask those of you that are more experienced in our class with driving in the 1970s, what was going on at that time? Well, the answer is oil embargoes. That's right. OPEC nations decided that they were going to withhold oil deliveries to the United States, among other countries. And so our president at the time had said, you know what, this is insane. We cannot rely on foreign nations to give us our oil. We need to become energy independent. So I am going to establish a new department. And so here it was, the U.S. Department of Energy, established in 1973. And the whole goal, they were established to help wean us off of foreign oil, to think innovatively, and get us to start using alternative energy sources. How good of a job have they done? Well, we're here already in many centuries later. We're now here not centuries. We are now here 4 decades later, more than 4 decades later. And we're getting more oil from foreign countries than we ever did before. So how far have we come? Well, in 1970, we were importing about 25% of our oil, whereas today, we're importing more than 60%. And that depends on who you ask and which statistics you look at. It's somewhere between 60 and 75%. The top import sources for us in the United States, the big 5 would be Canada, they're number 1, followed closely by Mexico and Saudi Arabia, and then Venezuela and Nigeria. That makes up the vast majority, 68%. And the next 5 would be Iraq, Angola, Ecuador, Algeria, and the United Kingdom, actually, of all places. So, it's kind of interesting that we have an agency whose job it is to get us off of oil, and yet we are using more oil now than we ever did in the 1970s. And that trend does not look to be slowing down. It looks to be continuing. And so one of the real problems with this reliance on foreign oil, is that we only have about 3% of the world's oil reserves ourselves in the United States. And yet, we have 25% of the world demand for oil. Well, that equation just is not going to work. You make up 25% of the demand, but you only have 3% to give to the world or to yourself. It forces you to essentially be an oil addict. We are locked in to buying oil continuously from foreign sources. So again, I want you to look at a couple of the videos that I have up on the course website. They will be very revealing about the view of politicians on the science around oil reserves, and how much of it we should or should not be using. We left off talking about carbon dioxide and its contribution to global warming and climate change, and we could focus on a number of gases actually that contribute to global climate change, but because CO2 is discussed so much in the media, I figured that we could focus on this. If you would like to know more about this topic, I urge you all to do your own homework on this and make sure that the source that you are getting your information from is an actual scientific outlet. The reason being that it's very easy to get the wrong information on this topic. Realize I would like to bring you all the way back to lecture number 1, where we actually discussed the scientific method and the importance of science and why it is that we tend to trust science. We trust science because it's based on evidence. Also remember that scientists cannot just make things up. We are kind of beholden by occupational requirement to base anything we say only on the weight of evidence. So that's where we're going to be picking this up now. There are many consequences listed here to climate change, and this is actually a few slides before where we left off. So let's go ahead and bump it forward here. Let's talk about the 4 main carbon sinks. And we noted here that there were 4 main reservoirs for carbon on the planet, and they're kind of discussed on this slide. The first one being the atmosphere. Everybody knows about carbon being kind of locked up in the atmosphere, but it's also locked up in the ocean, it's locked up in sediments, and it's also locked up in terrestrial systems, in the freshwater systems, in the plants and animals on land, and all of these reservoirs are trading carbon back and forth between each other through the carbon cycle, the natural carbon cycle, which is discussed in your book. And there are normal rates of transfer from one of these reservoirs to the other. And that's what these green arrows are kind of indicating here. I don't want you to memorize these numbers, but there are a few basic facts you might want to keep in mind. Number 1, the largest sink for carbon on the planet is in the sediment that is actually locked up in the rocks. And the ocean actually holds a great amount of carbon as well. The atmosphere is actually one of the smallest reservoirs for carbon, and CO2 does not remain in the atmosphere for very long. It tends to get transferred to the other sinks rather quickly. However, with human activities on the planet, we are actually contributing CO2 to the atmosphere faster than it can leave the atmosphere and get sequestered. So the net effect is that it ends up getting built up. And this is really where we left off last time, is talking about the sources and sinks of carbon. Sinks are those things that actually lock up carbon. That is, they pull it out of its gaseous form in the atmosphere and put it into something solid. So, for example, in photosynthesis, plants are actually removing CO2 and turning it into solid material, which can then be worked up through the food chain. Also, oceans. There are circulation patterns in the oceans that help sequester or lock up that carbon and put it into a depth where it is not going to escape and get back into the atmosphere. Plankton are also very important in this because they are also photosynthetic, and so they are pulling CO2 directly out of the water and thus allowing the ocean to continue to suck more CO2 in from the atmosphere. Now, while all of that is going on, there are also releases of CO2. So CO2 is also being given off by plants during respiration. Remember, they're only photosynthesizing when the sun's out. At nighttime, they are respiring. They are actually burning the sugars that they created during the daytime. However, you know that on balance, the amount of carbon sequestered through photosynthesis and the amount that's actually given off by plants in respiration, there is more that it gets sequestered. You know this because you look at plants and you actually watch them grow. As plants grow, they are actually accumulating carbon over their lifetime. Okay, so decaying, rotting organic matter also releases CO2, but the biggest release of CO2 naturally usually comes in the form of a volcanic eruption, like what you see over here, this picture. That is, all of that carbon that got sequestered over millions and millions of years into the rocks and into the sediments gets released kind of all at once. during a volcanic eruption. So a very small patch of CO2 on a global scale gets released all at once here in the volcanoes. However, humans are kind of changing this relationship here. Biomass combustion, that is burning of carbon-rich fuels like fossil fuels, burning wood is another example. Burning, and fossil fuels of course includes oil, natural gas, and coal. These are all contributing an unnatural amount of CO2 directly into the atmosphere. You think about how much time it takes to make fossil fuel. We discussed that when we talked about the origins of plastic. Well, that's a million-year cycle, or tens of millions or hundreds of millions of year cycle. The growing of a forest, so all of the carbon in trees in a forest, takes thousands of years to create. And that's true, by the way, for the wood, and then in the case of fossil fuels, coal, oil, and natural gas. When we burn them, we release all of that carbon all at once at a rate that's much faster than the amount of time it takes to sequester it. Another one of the real big releasers of CO2 into the atmosphere is actually cement factories. Cement factories are really all about processing lime. And lime comes from limestone. And limestone is really a calcium carbonate rich material. And the way that you make it, the powder that actually goes into cement, is made by superheating the limestone. And this process releases huge amounts of CO2. So these are the sources and sinks, and really what it comes down to is an imbalance. There are natural sinks, there are natural releases, and these things have been in balance for hundreds of millions of years. Unfortunately, we are changing that balance by contributing to more of that CO2 that is naturally stored in our sediments and in our high energy rich natural fuels, and we are burning them all at once and putting them directly into the atmosphere. So this is really the bottom line here. So this is kind of where we're going to focus, is the release of carbon, the fact that we're doing it faster than Earth can naturally sequester it. Okay, so I want to take you now to a time way in the past, in the mid-1950s, and this is the lead paper here in the journal Telus. You don't have to memorize any of this stuff. I did want to show you, though, the picture here that you see on the right is of Roger Revelle. And Roger Revelle was the director of the Scripps Institution of Oceanography down in San Diego. You may have heard of Scripps. If you haven't, it is one of the leading oceanographic institutions in the world. And they are highly reputable, and Roger Revelle was the guy who basically was running the show down there in the 1950s. Well, this is a paper that he co-wrote with Hans Suess, and this came out in 1957. There you see it right there. And this little excerpt comes from the abstract. This, and we'll read the title here. It's Carbon Dioxide Exchange Between Atmosphere and Ocean, and the Question of an Increase of Atmospheric CO2 During the Past Decades. So he was measuring CO2 in the atmosphere, and he started realizing that even in the 1950s, the amount of CO2 in the atmosphere was far higher than background CO2 levels in the recent past. So here's an excerpt from that. The increase of atmospheric CO2 from this cause is small at present, but may become significant during future decades if industrial fuel combustion continues to rise exponentially. So he didn't really know what the future held. All he knew is that if we continued to increase the amount of fossil fuel burning in the future, that ultimately it would lead to bad effects. And here's a more recent paper. This is actually by Sarmiento and Gruber. It's a team from UCLA who published this paper back in 2002. What they did is they looked at the CO2 concentration in ice cores. So one of the things that's really interesting is the amount of CO2 that is in the atmosphere right now. when snow falls, it actually captures some of that CO2 concentration and it holds it in a tight pack in the snow. And over time, that snowpack gets pushed closer and closer and closer together until it gets to be like tightly packed ice. And that means that throughout the ages, over the last many millions of years, as ice has fallen in certain areas where the ice doesn't melt, so for example, in Greenland or in Antarctica, these are areas that have been frozen. Certain areas have been frozen for millions of years, and every time snow gets laid down, it keeps a signature or a little echo of the past of the amount of CO2 that was in the atmosphere at that time. And some of the easiest ice cores to get to, I mean, none of them are really truly easy, but the ones that you can actually get to in Greenland that are really, really old, this team here, Sarmiento and Gruber, actually went up there and took ice cores and measured the CO2 concentration in the ice, and they were able to go back about 1,000 years. And this is what this graph is showing here, is that from about 1,000, that is 1,000 years before the present, from that point all the way until just about the 1800s, right about 1800, CO2 concentrations were very stable. They kind of fluctuated somewhere around 280. But shortly after 1800, CO2 concentrations in the atmosphere began to rise. And you guys recognize this graph here, right? This is a J curve. This is exponential growth here. So the amount of CO2 is actually growing exponentially. So what happened right around the 1800s? Well, this is the start of the Industrial Revolution, where our industry, our whole lives, everything about the way we live changed once we figured out that we could get an incredible amount of energy out of burning, at that time, coal, but eventually oil and natural gas. Now, they published this paper in 2002, so the data they present go all the way back to 2000. We have more data than this, though. You see, 280 was the average up until around 1800. Now, this graph here, they show it going up to 360, but that's old news. That's what it went up to in 2000. If we want to get a better sense of this, we need to go all the way up to 390. And in fact, beyond that, the present CO2 levels, even compared to this paper, what you're looking at from about this point on is what has been added since this paper came out in 2002. That is absolutely frightening. Now, at the same time that he's learning all of this, he's also hiring new faculty at Scripps. Revelle that is. And so Roger Revelle hires this guy right here, Charles Keeling. Charles Dave Keeling. He goes by his middle name. His name was Dave Keeling. Passed away just recently, a few years back. And Keeling's job was to fly from San Diego out to Hawaii on the Mauna Loa Observatory. Mauna Loa is the tallest mountain in the Pacific, actually, in the entire Pacific Ocean. And it's a great place for studying atmospheric events because it's so pristine. It's very, very far away from any human influences. So you know that what you're measuring in the atmosphere is truly a global average. And while he's at the Mauna Loa Observatory, flying back and forth from San Diego, he goes on a monthly basis, or he has his graduate students living there and measuring the CO2 concentration every single day. He sets up instruments to do this, and they average the numbers every month. And what you're looking at here is what has become known as the Keeling curve. And the Keeling curve is a monthly average CO2 concentration in the atmosphere. Each one of these dots represents a monthly average from 1957 all the way to the present day. So, notice how there's like a seesaw pattern here, up and down, up and down. What you're looking at is an increase and then a decrease, and then an increase and a decrease in the amount of CO2 in the atmosphere. It turns out that the plants in North America are able to draw enough CO2 out of the atmosphere by the end of the summer, let's say by October or so, that the CO2 concentrations drop. But that once winter comes around and spring, the plants die back a little bit. There isn't as much sunlight hitting North America and Northern Europe and Asia during the winter time, and so the CO2 concentration tends to increase in the atmosphere. So we do see this normal increase, decrease, increase, decrease. However, the trend over the decades has been up and up and up. Now, all the way back to May of this year, that is the value that we see right over there, 394.2. 394.2 was the high at that point. And these data, by the way, are current as of November 1st. November 1st. So, I take that back. These are current as of November 30th. November 30th. So these are very, very recent results. And I wanted to actually show you the website where this information comes from so that you can monitor this every single month for as long as you want. But again, just to remind you, it was 280 parts per million back in 1850. Okay. So here is the actual website I refer you to. This is a website of the National Oceanic and Atmospheric Administration. They are the government, the U.S. federal government agency in charge of monitoring the weather, monitoring climate, and all of that kind of stuff. And this is the CO2 concentration measurement device that is currently mounted on Mauna Loa Observatory. And this is just for the last 6 years or so. And notice that it always peaks more or less in May, and then you see this drop. And here's kind of where we're at right now. So my question to you is, where are we going to be in May of 2012? Well, if you just draw a line through the peaks of all of the past years, and this is just a rough line, this kind of puts our dot for May of 2012 right at about 395 or somewhere above that. So you guys will have to check it out for me. Come back in June 1st of 2012 and see if I was correct for that May result. That would be really interesting, wouldn't it? Okay, so this argument is raised by a lot of naysayers in the media about those things that might cause CO2 to naturally increase, and they cite a lot of climatological historic data that it turns out is correct, but they misuse that information, and the problem is that the public is usually not informed enough to be able to determine what is good information and what is bad information. So let me explain to you what the quote-unquote natural warming of our planet would be a result of. It's actually the result of Earth cycling that was discovered by an astronomer by the name of Milankovitch. And Milankovitch developed these mathematical formulas to explain the movement of Earth around the sun. Turns out we do not go around the sun in a round pattern. We actually fluctuate, and we fluctuate around the sun in three very distinct ways. The first way is a process called eccentricity. Eccentricity is an understanding of how the orbit of Earth around the sun changes. At times, our orbit around the sun is more or less circular, in which case, at all points along the circle, we are about the same distance from the sun. However, on occasion, our circular orbit begins to take on a more oval orbit. When it takes on an oval orbit, there are going to be times when we are much further away from the sun and much closer to the sun, and all variations in between. When this happens, the Earth will get an unusually high amount of sunlight, and at other times an unusually low amount of sunlight. So this would be an example of a high amount of sunlight because we are much closer to the sun. Here would be a lower amount of sunlight. And this variation here in the orbital eccentricity of our planet follows more or less a 100,000 year cycle. That is, every 100,000 years, we go through this cycle of being very circular to very oval to being very circular again. The second Earth cycle, or the second Milankovitch cycle, is called the obliquity axial tilt. And many of you already know that Earth is actually tilted on its axis. We spin at a slight tilt around when we're orbiting around the sun, and that is what causes our seasons. But that tilt actually has a wobble to it. Right now we're somewhere around 23 degrees, that's our axial tilt, but historically this axial tilt will vary from about 22.1 to 24.5 degrees. When that axial tilt is greatest, 24.5 for example, that means our seasons are intensified. Much colder winters, much warmer summers. When that axial tilt is not so intense, so 22.1, then we have much milder winters and milder summers. Now the third way is something called precession. Precession means that the actual axial tilt itself is rotating, and it spins in an entire circle, and for it to go all 360 degrees takes about 26,000 years. Oh, I should mention, by the way, the axial obliquity, that variation there is on a 41,000 year cycle. Okay, so at any given time, because of any one of these Milankovitch cyclings, we could either increase or decrease the sun's radiation as it hits the planet. When you factor all three together, you can actually generate a very interesting curve that very easily predicts why it is that we had ice ages and warming periods throughout our geologic past. Kind of interesting. Let me show you what that looks like actually if we were to graph the amount of CO2 that we have in our atmosphere for the last 650,000 years. 650,000 years, because this information is coming from ice cores and mud cores. And so far we are getting really, really good, by the way, at drilling through ice and drilling through muds, but we still can't quite get much beyond 1,000,000 years when it comes to CO2 patterns. Hopefully, with some new technologies that will be implemented in the next decade, we'll be able to go a little further back in time. But for now, we have a pretty darn good record, all the way back to about 650,000 years. 650,000. And what you're looking at here is the amount of CO2 in the atmosphere and the subsequent temperature on the planet. And you'll notice the dips. You guys see the dips right there? Those are consistent. Those are consistent with Milankovitch cycling, and it predicts the 7 ice ages pretty darn well. And we also have 7 warm periods in the last 650,000 years. Again, very consistent with Milankovitch. And what people might say is, oh, well, look, right here, we're in a warming trend. Isn't it true that we're just probably on the tail end of a normal warming cycle? Well, yes, only up until about 1850. You see, I have conveniently left off the part of the graph that includes 1850 to the present. Let's go ahead and add that. That's what it looks like now. This is not consistent with Milankovitch cycling. In the summer of 2011, we hit 394.2 parts per million in our atmosphere, and in the last 650,000 years, our CO2 concentration on the planet has never even come close to that. So this is why scientists are so concerned, climate scientists in particular, but not just climate scientists, geologists, biologists, physicists, chemists are all very alarmed by this. And so this is not in dispute. There is not a single person, a qualified, bona fide person in science that disputes these findings. And this is also not based on just a single paper. This is based on mountains and mountains of evidence, all pointing to the exact same culprit. These are not scientists. They're all colluding with each other, calling each other on the phone, and telling each other to forge their data or to make stuff up. Everybody is arriving at the exact same conclusion to the problem. So, It is a scientific consensus. The fact that the Earth is warming and that humans are to blame is not controversial in science. It is only controversial outside of science. Is there a data controversy? No. There is no controversy about the data. While scientists may disagree on small things like how the data are collected, people might demand that the data be a little bit more robust in one area here or another area there. The overwhelming mountain of evidence is such that nobody disputes the overall theme here, the overall message. Now, is there a political controversy? You bet there is. So, what do? This is you. You know, you're not going to be a climate expert in your life. Maybe you are, but probably not. So, who should I believe? Should I believe the data? Should I believe the scientists? Or should I believe the politicians that are telling me one thing, or the newscasters that are telling me something else? Well, let's go back to science, to our discussion of the scientific method and of evidence in general. Remember, we don't believe in science. We don't use that word because belief implies that we are accepting something with no evidence at all. So this is actually just a trick question there. Well, let's cross that out. Really what you need to say in science is, what should I trust? You should always go with the argument that contains the most evidence. In science, we are an evidence-based method of gathering information. So, what should I trust? You should trust the evidence. That's what you should trust. And so, in light of all of this, here's a quote from Mark Twain. It's actually kind of sad because even back in the days of Mark Twain, people understood this about the human psyche. What gets us into trouble is not what we don't know. It's what we know for sure that just ain't so.